So we had some broken audio on Tuesday, and I apologize for that. So here's my attempt to kind of re-record, mostly distill down what we talked about on Tuesday. Some of the interactive aspects I won't be able to recreate, but we can get the general gist of what we talked about on Tuesday. Where we had left off was talking about the different flavors of Axie. And I think ultimately, the one thing I wanted to accomplish is to increase just your awareness of what's happening with these IP cores that we're going to have in our design as a general philosophy, how we want to communicate amongst a bunch of shared resources, and then in practice, what that means in our Xilinx Vivado based designs that are using this Axie bus. We talked about the full Axie and the different channels associated with requesting reads, requesting writes, getting responses back, and sending data in that direction. And we started talking a little bit about what a state machine would look like for that controller. And we left off last week saying, well, we could build such a thing. It would be a valid assignment. Generally, I've provided that for you when we do need that in our lab assignments this semester. And you need to be mostly aware that this is happening. This is something you'll have in your design. You're going to be seeing a lot of these signals because there's a whole bunch of them for reads, for writes, and then for the response channels as well. And then we talked about the Axie Lite as well. That one may be a bit more relevant for us because it's just a subset of the full Axie, and it's useful in those scenarios in which you don't really care as much about performance. You just want to have a memory mapped way of accessing your peripheral for configuration, for status, and for things of that nature with your IP core. And we're also using that. Specifically, we're using that this semester because we want to be able to provide configuration registers for the various IP cores. You're already maybe seeing that as you dive into your viewport and your render output cores, that they have all these registers defined. That little block of logic is auto-generated by Xilinx, and that's for Axie Lite. So that gets rid of some of the nicer features where you can have protected access and you can tag things as cached and you can have long burst accesses. All that's not there in the Axie Lite version of the standard. But what you get is a nice, simple interface and significantly fewer signals to have to wrangle. You'll be seeing that code and editing code that uses this Axie Lite interfacing. It's a nice compatibility layer that can get generated as well. Because all the signal names are roughly the same, when you go from an Axie full interface to an Axie Lite interface, the tools are going to be smart enough to kind of build those transceivers between one and the other. Strip all the burst transactions, sequentialize all of those out so they do them one by one. And so your IP core is none the wiser that there's a full Axie bus master on the other side of that connection. More pressing for us in terms of what the actual logic you'll be designing is this third flavor of Axie. This is the Axie streaming. So you'll see the Axie S prefix in a lot of the signal names. That's referring to a third version of this. It's Axie streaming. It's got the same name. It's in the same interface family, but otherwise there's actually not all that much in common. First off, it doesn't have an address phase at all. Everything is just for a point-to-point connection. So that diagram we have here where you're seeing the master interface and data flowing to the slave interface, that's always going to be the case. There's no shared interface happening here. It's a point-to-point connection that's happening here. So we don't have to specify an address. We don't need to because we know exactly where everything is going. It's going to that other side of the physical connection that we have here. So it's FIFO style, and in fact, when we looked at the FIFO generator, one of the options was to generate an Axie stream FIFO, and it has much simpler signaling that, at least in theory, doesn't require you to have any sort of FSM in your design to do that interfacing. There's that two-way handshake going on here effectively. We have a valid signal to signify I'm ready to send data. We also then monitor, coming from the opposite direction, the ready signal. That's from the slave side, the receiver side saying, I am also ready to receive data. And when both those signals are high, that should indicate that we have some valid data that can be transmitted. And both sides need to be aware that's happened. At some point, the master side of the transaction wants to send a lot of data values. Perhaps the slave side can only handle a few at a time. It can then set that its own T-ready line low to let it know, wait, pause. Like a FIFO that's full, for example, we can't accept any more data. Let's wait until we are ready for any more data to get transmitted. There's a lot of other signals there as well. If you look at that description of T last, it's a little ambiguous, right? T last indicates that this data packet we're transmitting is the last one for now. Well, what does that even mean? And the answer is, and same with the T user and T ID signals, those are very much system dependent or application specific. What we want T last to mean is up to us. It's commonly used in the Vivado ecosystem as indicating end of a frame of video data. So we'll use it roughly for that same purpose. Our vertex fetch module will toggle T last when the last vertex has been sent for a given request. And we can choose to use that how we see fit. Or if it's always 0, that's also perfectly fine. It's useful for when interfacing with a VGA style controller, right? To say, this is the end of the frame, start your vertical retrace, and don't expect any more pixels until we're done with that retrace. That's a common use for it. Same with TUser and TID. We get to decide if we want to use those signals for anything. The spec works just fine if you're not using them at all. So you really just need ultimately T-valid, T-data, and T-ready. So we had an in-class exercise when we did this the first time around, where we looked at a relatively straightforward IP core. I called it the AXI-S inverter, and looked at what it would mean to build this IP core that just inverts an 8-bit data bus value coming in over an AXI stream interface. Even though the VHDL was relatively straightforward for this, I think a couple takeaways are still pretty important. First off, the naming convention for those signals is still pretty important. Even in this, I'll call it a relatively trivial example of an IP core that's AXI stream compatible, we still have to be pretty conscious of what we're naming those signals so we don't get confused along the way. And you'll see this a lot, that we want to define something, if this is a pass-through core, that on the streaming side of things, everything is AXI-S, but we also prefix it with, this is my read interface, that's my slave interface, S underscore. It doesn't have to be that, but that's just one way we can certainly do it. Likewise, on the downstream side, that would be prefixed with M underscore, AXI-S related signals here. And so you may kind of start to get that backwards if you're not careful, right? This is an IP core that's kind of passing data through. Your viewport core is also passing data through. So it's both, right? For these point-to-point connections, it's both a receiver, it's waiting to get data, and it's also a sender. It's going to be sending data downstream. I sometimes get upstream and downstream backwards, but it's good enough for our purposes. Data is flowing downstream. So it's both. And so you do have to kind of keep track of what are the signals that are my input ports and what are the signals that are my output ports. And the only place where there's really a gotcha, where sometimes your code's just going to look wrong, but it's actually going to be correct, is that everything's flowing downstream. It's from master initiating, except for that T-ready signal, right? That is coming from the slave side. So that's an input port on the master interface, and that's an output port. My core has to tell the upstream core that it's not ready. Likewise, my core has to listen to the downstream core when it is not ready. So even though the VHDL for the pass-through can ultimately be really trivial, the one example we came up with in class was this one, where it was just a pass-through. Pass through the T last, pass through the T valid, invert the T data, because that's just what this IP core is doing. That ready signal is also a pass-through, but the direction of it looks kind of backwards. Somebody asked in class, hey, is that not a typo? But it's actually not a typo, right? I have to monitor slave side connection for T-ready and pass that back upstream. That's why that looks like the signal's going backwards based on our common naming convention. Your logic's always going to look something like that. Another variant of the design was also perfectly valid. This was like a two-state state machine, where in state 1, we're ready to receive data. So we're setting, when we're in this state, not all the code is here, but it's close enough. Check to see that set T ready, we are ready. Only when that valid is high, we then grab our data, store it in a register somewhere, and go to our send state. And in our send state, we're ready to trigger the data. So we do the inversion in our VHDL. We set T valid, we pass through T last. Only if that downstream T ready was high, did we actually send the data through, we can go back to our receive state. Performance-wise, there's a bit of a trade-off in between this design and this design. This is just combinational logic, so this is just pure pass-through. That's probably higher performing in the sense that there's no extra clock cycles required for this. This one maybe is getting 50% ideal bandwidth, right? Because it's taking 2 cycles to do that single transaction. The downside of this one could be critical path, right? If it's an inverter, who cares? That's not going to affect our critical path too bad. But if this is doing some complex math, a combinational pass-through may not work. We may need some kind of thing like this. You can also build pipeline, sort of data flow pipelines for doing these AXI stream controllers. you do have to be a little bit careful. You'll see logic in data flow that looks like this, which is valid. When we're in the receive state, set T ready high, so you don't actually have to do it in your state machine logic. Data flow is not magic, right? This is the equivalent to a one-line process block. You just have to be a little bit careful. First off, be careful that you're not doing both. If you're setting this here in a data flow line, don't also be setting that same signal in your process. The logic may be consistent, but if it's not, you're going to get multiple drivers and you're going to be in a bad place there. Separately, if you're trying to pipeline these ready and valid signals through, you got to be a little bit careful. You can't assume both upstream and downstream are going to be in perfect sync with each other. There'll be different bottlenecks in the system. Sometimes we can try to estimate where those bottlenecks will be so we can have some knowledge of, well, if upstream is busy, then downstream is not going to be busy, or vice versa. But if we can't guarantee that, we have to be a little careful with pipelining those signals because we don't know that just because T valid or T ready was high now doesn't mean it's also going to be ready next cycle. There's no guarantee that that's the case. So when we're pipelining and if we're building deeper pipelines, you may want to look up this concept called a skid buffer to be able to keep track of those signals because we're kind of pipelining in two directions at once, right? You can't see my hands, but we're pipelining T valid in one direction and we're pipelining T readies in the other direction. And so we just got to make sure everything's in sync there. It's a little bit tricky if you're trying to build a pipeline. I always say my philosophy has always been whenever one of you comes to me with something that sounds really clever, I say, stop, don't be clever. Let's start with functioning. This will be your easiest path to a functioning design for your viewport controller, for your IP core, for the viewport axis stream controller side. So get that working. If you've gotten that working and you feel like really ashamed that you're losing 50% of your potential pipeline bandwidth, okay, then start to look at improving upon it. Starting from a working design, then you're in a good place. You have something working, you're only trying to make it better. That's better than trying something complicated at the first step and just adding complexity on top of what's already a pretty complex assignment here. We also talked a lot about bus arbitration. The discussion got a little scattered when we tried it on Tuesday in the first place. But the big picture here is you need arbitration when you have multiple masters on a bus trying to access the same resource. This is shown as two CPUs trying to both simultaneously send data to a GPU. It doesn't have to be that. It could be two IP cores that are mastered on an AXI bus trying to copy or read data or send data to a slave on that same AXI bus. It's the bus itself that is the shared resource in that case. And that's the role of an arbiter. It's to determine that when there's multiple masters trying to access a bus or some resource simultaneously, that only one of them gets what they want. And it has some sort of heuristics or some sort of algorithms that are put there in place to say when there's a tie, when two things want access to something, who gets it? And there's many different approaches. We really just kind of scratched the surface of what is possible here. We talked a little bit about daisy chaining, where if our real priority here is to minimize the amount of wiring required. If you look at your I2C interfaces, that's basically a daisy chained approach. What you can do is have a shared bus request line that any of these components that are sharing that bus share also that physical line here. And it's the grant signal that is daisy chained from component to component, where it's one physical line that is both an input and output as part of the spec for each of those individual devices or bus masters. And there's a physical proximity here that the device that's physically closest to the bus arbiter would have the highest priority. If a request comes through, the grant line would be toggled when the bus is actually ready or the resource is actually ready. If this IP core or component or device needed the bus, it's done. I requested it, I get highest priority, I have it. If it didn't need it, then it just forwards that signal on. Likewise for this next one. Did it need the bus? No. Let me forward it on. D3 did need the bus. It stops. The line stops there. That's the chaining of devices, the daisy chaining of those devices. Well, the advantage is already there in terms of simplicity. Your wiring is much simpler than having this centralized, independent requesting mechanism. The downsides we talked a little bit about. It's not necessarily fair, right? Fairness is a formal term in this field in terms of what is a fair heuristic, fair algorithm, but this wouldn't be it. This component, if it needed the bus, if it wanted to dominate the bus, could dominate the bus the entire time. So these kind of lesser components would be out of luck if D1 always wanted it. And there's a little bit of a reliability issue with daisy chaining as well. If D2 is broken, something's just wrong in the logic. D3 and D4 will never see that grant signal. They're effectively broken as well. So the advantage is it's simple. If I wanted to add D5, I literally just add 2 wires to my device and I don't have to change any of these other components. Same with D6, D7, etc. But if D3 is broken, we're in trouble. And likewise, we have that fixed priority, which can be considered a little limiting for a design like that. We talked separately about having just separate independent bus requests and bus grant lines for every device. There's a lot more lines than when that's the case. We talked about polling approaches where you actually can have shared bus request lines and then a poll count line, which would be some sort of counter, some sort of algorithm that would determine which IP core would get access to the bus at any given time. And each of these components themselves would then be programmed with some ID saying, I am D2, maybe my ID is also then 2. When the arbiter wants to provide access to 2, it would just set the numeric value of 2 on those lines. That would allow for arbitration to be as simple as just an up counter. That would be an equivalent of a round robin arbitration scheme where 0 gets it, then 1 gets it, then 2 gets it, then 3 gets it. If you miss your turn, well, you know your turn is coming up relatively soon. That's some version of fair. And when we talk about the AMBA-AXI interface, it actually doesn't really talk at all about in the spec how that arbitration should happen. But given that we have these kind of separate valid and request lines for all of the different phases of our transactions, it strongly hints that a separate centralized solution would be in place for all the IP cores that you have connected. There's 2 different IP cores Xilinx uses for this purpose. We took a look at them in some depth in our Vivado project. There's the AXI interconnect as well as the quote-unquote smart connect. And I'm using each one in this starter project you have for 2 slightly different purposes. The first one's here in the memory subsystem, where the shared resource that we care about is the actual memory interface. The Vivado project doesn't show a lot of the gory details of what's happening with their DDR3 controller. We kind of encapsulate all of those signals into just a bundle called DDR3. And the real messy logic is happening in this memory interface generator component, which we don't touch, you don't touch. It's got a lot of the low-level timing characteristics of the physical DRAM that this FPGA is physically connected to on our Nexus video board. But we know that there's multiple components that want to be able to read and write from memory. And so we would need to have our arbitration scheme as well as a bus decoding scheme. And that's what the quote-unquote smart interconnect core gives us here. In this case, in the version of the project that I'm working with, there's 7 different IP cores that want to be able to read or write from the main memory, from our DRAM memory. So you can think of those as being 7 bus masters connected to just the single bus slave, which is what's going to connect to our memory interface here. The labeling, like it looked before, may seem a little backwards to you. Who is the master and who's the slave is a relative term, right? There's 7 bus masters. This interconnect is then a slave to all those connections because it has to handle all those connections and return just a single response back. Likewise, it then would connect all those requests to just one interface here for which it would be the master on that connection happening here. So this has to handle arbitration in some way. And we talked a lot on Tuesday about, from the frame buffer's perspective, that arbitration is pretty important here. If we look at the various connections to our memory, of which the frame buffer is the primary purpose of having our memory in the system, one of those connections is going to then connect back to the video subsystem. It's this one actually right here. One of the connections is just a DMA. If we want to do some block memory transfers, that's one way to do it. In our video subsystem, we have a core whose primary responsibility, which is also a type of DMA core, is for making sure we get the next image on the screen 30 or 60 or however many times per second. And it's going to talk to all the logic for the VGA controllers to actually spit out, in this case, the right HDMI signaling to give us the right colors on our screen that we're connected to. That's one port that we're sharing amongst our multiple connections to our memory, ultimately our frame buffer here. So from an arbitration perspective, this one's pretty important, right? This one should have really high priority on that interconnect. Think about it from this perspective, right? We talked about the double buffering. We didn't talk about all the details of that, but how there's two frame buffers logically in memory. One we're always reading from to display the screen, and one we're writing to update what we would like to display on the screen. And the reading process should always have higher priority in a fixed fashion. If our writes are slow, if we're not writing to memory as fast as we would like to, we're going to wind up having effectively dropped frames. Our app isn't updating the screen as fast as we would like. If our VDMA gets blocked, if our VDMA doesn't have priority to read from the frame buffer, well, unless we're really careful in terms of how we buffering and what fallback modes we have, we're going to have invalid HDMI signal on our screen. The whole system's going to break if that doesn't get to read the pixels from the frame buffer as quickly as it needs to. So having some priority there is an important thing. We really have to give the VDMA full access to the bus when it needs it. And we can configure that in the Smart Connect itself. Separately in this system we have here, we already looked at this briefly in what I labeled as the system interconnect. There's not a lot in that other than a DMA block, a separate DMA block for just doing block transfers. And now we have a much wider looking switch here that's handling arbitration. There are 3 bus masters that are wanting to access. And what we have this is more than in your MP1 design, but you'll keep adding to this go, a whole bunch of, in this case, 14 different IP cores we're connecting to the bus here. Anything that we want to configure over the AXI, that's the path that it's taking. In terms of the masters, you're not actually using too many of them this semester. The first one is going to connect to the Ethernet subsystem. That's where the driver is going to come in, right? OpenGL code triggers calls in our driver. It's going to trigger Ethernet UDP packet sends. That's going to wind up on that highlighted wire there. That's what's going to allow us to configure and read status from all of the cores in our system that are connected to this interconnect. And this also connects to main memory as well. So this lets you spray data all throughout your entire system. The second one is for, there's that DMA. So if we want to do block transfers, it's nice to have that ability there. The third one is for a microblaze processor we actually have in the design. I call that the debug subsystem. It can be useful if we want to write code resident on the board itself to read from the IP cores, to do all the same kind of steps we could do here. We made the design decision early on that we didn't want to be running an operating system on this chip directly, and to go with our workstation running OpenGL, driver sending data over the wire, versus everything being resident in a microblaze processor on the chip itself. When you take, and those of you who have taken CPRE 488 or are taking it right now, your view is going to be more self-contained because you'll have, it's an ARM core in that case, but you're going to have this processor that's a bus master in your system, and all of the code you're writing is going to be resident on that processor. We could have done that this way this semester for this class. I liked this approach more. It allows us to do anything we want with OpenGL without having to be beholden to a Linux dev environment on this board itself. So in this case, though, because of that, the layout looks quite a bit different than our memory interconnect. We have just a few of those bus masters and a whole bunch of those bus slaves, because we have just a lot of different IP cores that we're wanting to connect to the system. So arbitration also potentially becomes important there, but at least for our purposes, outside of some of the memory copies we may want to do, our Ethernet gets access and gets the priority for that particular system. Separately from the arbitration issue, which is very important, the other thing that happens in those interconnect blocks is the address decoding. If you think back to CPRE 288, and certainly if you're doing 488, it's chock full of this kind of thing. A key concept in that class was address-based access for IP blocks. Memory mapped I/O is another term you'll hear used, where everything in your system is a memory address. Certainly memory is its own set of memory addresses, but all the IP, all the controllers, all the ADCs, all the other things also would correspond to some set of either registers that would have an address associated with them or memory addresses in your system. And the Vivado method of system-based design is very much that as well. You don't configure it directly in here for whatever reasons. There's a separate address editor tab that pops up. And here you get to view and change the address mapping in your system. There's a lot going on here, and the nice thing at least is right now you don't have to change it all that much. You're not adding new cores. You shouldn't be changing it at all right now. But the idea is that interconnect component is doing two things. It's arbitrating requests to the shared resources, the slave side of the bus, between the different masters that we have here, and it's determining how to route requests that come in. We create a UDP IP packet. As part of that, we're setting the AXI write or AXI read address. This interconnect is then looking up that address in what effectively gets generated as a really big table here and determining which slave port that physically would correspond to. You're seeing memory regions of the range of 64K as a minimum here. We can make it smaller. You keep it a power of 2 anyway because that makes the actual decode logic as simple as looking at just an individual bit of the address that comes in. This looks a little messy because these IP cores were made by different folks. Some were made by engineers at Xilinx over a period of years. Some were made by engineers at Digilent, who manufactures the board. Some were made by me. And it's all referring to the same thing. These are all just slaves on the AXI bus. Some of them are really explicit the fact that they're AXI light interfaces. Others are AXI light interfaces and just don't use that term for whatever reason. Others are explicit that they're AXI full interfaces, but they're all speaking AXI. So they're all doing the things we talked about in this topic here, and they all have an address range associated with them. These were all auto-generated, but what we do need to do is pass that information between the Vivado project and the driver that's interfacing with this. All ARM-based designs, if you look at the bootloaders for ARM-based systems, including every one of your cell phones, that's a big part of the boot process for it, is determining via a little text file and ultimately a binary blob describes it, what are the IP in the system and what addresses are there at. Right now, we do it via just hard-coded in SGP system.c and SGP graphics.c. There is a way to export a header file that basically pound defines all these ranges for us. We didn't have a good way to kind of integrate that cleanly into the rest of our driver infrastructure. So right now, since we're not changing it all that frequently, we keep these fixed and we update our driver as need be, right? A driver change takes a minute to test. Changing any one of these values takes 30 minutes to an hour to test because this does require a synthesis rebuild, a bit file rebuild when you change any of these values. But then this is where you can see that kind of glue logic in the driver. I want to potentially send a value to my viewport core. Somewhere in the viewport core, there's those AXI light registers, and those are going to be configured as an offset from the base address. What those offsets are something you get to determine, both in the header or the .c file for the driver, as well as which registers you physically put this various information in the core itself. I set some for you to start with. You're probably okay just sticking with those, but that's what's happening here. So from the driver, we realize we need to write a value to our viewport X width parameter that's going to correspond to an address in memory for which it's going to be this base address plus whatever number of byte offset corresponds to register 3 or whichever register that we have act as in our design here. Then the AXI interconnect, that block, is going to determine that the UART the Ethernet controller wants to access the bus. It wants to write a 32-bit value to this address. It should give it access to the bus, and it should forward that request on to the viewport core that you have here. And that's something that's hard to test in simulation because you're not simulating the entire system in that sense. And it's a little hard to test that it's happening on the board. That's where the ILA comes in, where you can start to actually check that. It'll be easier to check that via software, to have readable and writable registers, and to just pull those registers in software and see what are the values of my configuration registers. Am I getting debug information back out that makes sense to me? But different approaches may work depending on your team's personal workflow. The only other gotcha here is that the Vivado interconnect infrastructure allows you to set different address ranges for every master on the bus. And that's why there's a whole bunch of stuff going on here. This one, and hopefully you have a little bit of write-up about this, is the AXI memory map to stream converter. This is what connects our UART, our Ethernet code to the AXI main bus. That has its own set of address ranges. The Microblaze has its own separate set of address ranges for those, as does the DMA core we have there as well. I explicitly keep those all the same and very carefully make sure that they're all exactly the same values for this block as well as for this block. It's not required that they be the same. You can have a separate decoder lookup value for every master connected to that switch there. I've never seen the use case for that. I feel like that would only lead to some confusion along the way. For our purposes, we have a 32-bit address space. A decent chunk of it is dedicated to the main memory. That's 512 megabytes of our 4 gigabyte address space. That still leaves us plenty of address space to put things wherever the heck we want to, as long as we keep track of them both in this project as well as what we're doing in our driver. You should be able to access our components and do the interfacing we need to do. Well, I sure hope the audio for this recording actually worked out so I don't have to do it a third time. Otherwise, I'll jump back and see how things are going with this week's lab. You should be making a lot of progress on the hardware side. It's going to be hard to really test that on the board until you also have some of that driver stuff working. So, getting the team back together and making sure you're ready for full system tests is a pretty important critical stage as you work on the labs this week. Good luck with that, and I look forward to seeing your progress.